Hello, everyone. I'm Apurva. I'm part of the anti-abuse infrastructure team. And in this session, we are going to talk about um, the overview of trust and privacy filtering and how we leverage Venice in one of our recent re-architectures. So this filtering platform has been through three generations of re-architecture. So we are going to talk about the second generation and the third generation and how Venice helped us make this filtering platform more robust and stable. So the agenda would be a brief overview of the filtering platform, how restrictions and privacy filtering works at LinkedIn, what was the second generation, what were some of its shortcomings, and major production incident which was caused due to some of the shortcomings of the generation 2 architecture, and how we launched prototyping using probable candidates for the next generation of re-architecture. And finally, how we re-architected using Venice and what were some of the major events after we did the migration and re-architecture. So trust and privacy filtering platform at LinkedIn is responsible for ensuring um, the genuine users have a good experience on LinkedIn. They don't get to see bad influence from confirmed harmful and malicious actors. And it is also responsible for ensuring the privacy settings and actions that users initiate. So example could be member-to-member blocks and account states like hibernation and memorialization. So here are some numbers which define this platform. And the kind of integration that we have with various product verticals like feed, comments, articles is basically on render time. So for example, if you load the feed, we'll get a lot of calls. The enforcement system will get a lot of calls from all these different product verticals. And since this call is in a critical workflow, we have to ensure we are able to serve large QPS at a very small latency, because any increase in latency will have cascaded multiplier effect on the site load speed. So we right now have 165, more than 165 product vertical integrations, and we serve 6 million plus QPS. And we have a strict SLA of 4 millisecond P99. The total number of restrictions we have is 200 million, and it includes various types of restrictions, each for different kinds of community policies that are being violated. And regarding the call pattern that we get from our clients is basically we have batch APIs. Depending upon the integration style and the use case for the clients, the maximum batch size that we serve is 30,000. And this adds more to challenge of maintaining strict SLA because of long tail latency. So this is the generation 2 of the architecture. Here we have the data management system where user initiated actions like member to member blocks or hibernating your account can ingest data or add new kinds of restrictions. And also we have several abuse detection systems which are nearline, offline or online workflows using static rules, dynamic rules or machine learning rules to identify harmful actors on the platform and restrict them. Once we identify bad actors, we need to create restrictions for them. So we have several separate espresso tables for each of the restriction types. And these generate Brooklyn streams. Brooklyn is basically Kafka-based real-time streaming platform used widely inside LinkedIn for communicating between data infrastructures. So we have separate Brooklyn streams for each kind of restriction types. And inside the enforcement system, which is a read-only high QPS, high throughput system, we have fast util data structures for each kind of restrictions. So these Brooklyn streams initialize the data structures and make sure they are updated with latest change captured. And during render time, the product verticals call the enforcement system for filtering bad actors. So the API takes in the author of the content and the viewer, and based on the restrictions between the author and viewer and privacy settings between both of them, we decide whether to filter the content or not. The Brooklyn stream itself, we like it is done in two parts. First, we do bootstrap Brooklyn stream, which ensures the data from the snapshot espresso tables is ingested first, and that includes bulk of the data, like around 99%. And then we switch to change capture, which makes sure the ongoing updates to the espresso tables are captured by the enforcement system. So yeah, this architecture had some shortcomings, and some of them related. Some of the shortcomings caused a major production incident, so that we are going to cover next. So the first shortcoming is high bootstrap time. We wait for the bootstrap Brooklyn stream to complete before taking in traffic. And we also tried several optimization efforts in order to reduce the bootstrap time, but the best we got was 35 minutes per host. One of the optimizations we tried was partitioning the Brooklyn stream to increase parallelization, but we couldn't beat 35 minutes. The second one is a bit related to the first one, which is high lead time for changes. So for any change or fix that we need to push in the enforcement system, we had to wait for more than 10 hours per data center. And the reason for this is we had a deployment concurrency limit of 25 hosts at a time out of like large number of hosts. Currently, we have 450 per fabric per data center. So since this concurrency deployment limit is absolute and not percentage of the host, it poses another challenge, which is the lead time will actually increase with organic traffic growth in LinkedIn. So for example, let's say because of traffic growth, we add 50 more hosts, which means two more iterations of deployment, adding 1 hour more to lead time changes. And since these data structures are stored on heap, they are prone to GC during the resizing, especially when it is in steady state serving live traffic. And if the data structure is big enough, it would lead to stop the world GC, where all of the CPU cycles is consumed by GC in order to free up enough space for resize. We also started seeing a lot of instability due to stuck partition issues. There can be two kind of problems with this. If the bootstrap frame is stuck, the application is not able to boot up and announce to load balancer and take in traffic. If the change capture stream is stuck, we serve stale data, which in itself can be a risk to LinkedIn. So this is an overview of a major incident that was caused last year, especially because of the stop the world GC occurring on all the hosts. So because of organic growth of LinkedIn, we saw an increase in a huge spike in the member-to-member block data set, and this breached the load factor capacity threshold, triggering a rehash. And this rehash required 2 GB of contiguous block of storage. So application wasn't able to find this easily, and it needed to do unfragmentations and move some blocks of data. So it triggered a stop the world GC, which lasted for a few seconds. This itself caused the request to get backed up, and coupled with thread pool thrashing. Um, the issue was finally recovered after load shedding was kicked in by the LinkedIn's load balancer, which allowed time to clear the pending request. So the issue lasted for 30 minutes. So this nudged us to explore some internal technologies and see how we can make the system more stable and avoid such risk. So we had two promising candidates. The first one is Bloom filter backed by distributed cache, and the second one was DaVinci, one of the Venice clients. So we'll cover the Bloom filter one first. Just to give a quick overview of Bloom filter, it is a highly space efficient probabilistic data structure, itself containing a large bit array and few hashing functions. So during the data ingestion part, let's say we try to add A, the hashing function would return the slots in the bit array where the bits need to be set to 1. Similarly, for B, when we try to insert it, we set bit 4 and 9 as 1. During data lookup time, we do similar operation where we pass in the element to um, the hashing function. And if the slots returned by the hashing function are all one, then the Bloom filter returns true. So it can return false positive, as you can see in the example D. And another problem with Bloom filter, traditional filters is it is not very trivial to remove elements because same slot is shared by multiple elements. The probability of false positive can be controlled depending upon the size of the bit array and hashing functions used. For our prototype, we used a simple Bloom filter where deletion was not allowed, and probability was quite less, like 0.01. So in the prototyping, um, we created additional host where we launched the prototype experiments. We use the Brooklyn stream as in the second generation to initialize this Bloom filter. And if the Bloom filters return true, then we made the remote call to do a cache lookup. The second type of prototyping that we did was using the DaVinci client, which is a eager cache which stores data either off heap or on disk. So we used the off heap one because it had lower latency, which we required. And we subscribed to all the partitions of Venice. So this ensured we had all the data in all of the hosts. We were not consuming like a subset of the partitions. The Venice store was initialized using Venice push job using some HDFS dataset, which was generated using source of truth espresso tables. So this is comparison of the two experiments. Latency was quite comparable. DaVinci had lower latency, and it was slightly higher than generation 2 itself because generation 2 was using on-heap caches. Um, One interesting observation we found was 25% of calls for Bloom filter were requiring remote calls. This was unexpected because the total percentage of LinkedIn members that have some kind of restriction is quite low, like 5%. But because the clients are calling us with large batch sizes, at least one of the members in the batch call being restricted was having high probability. So because of high percentage of remote call probability, this introduced possibility of instability due to network issues or even calling a new service. In terms of operational overhead, a Bloom filter in itself, like maintaining the Bloom filter, ensuring it has correct data, the Bloom filter is consistent across host was a challenge, and it also we were not able to avoid the Brooklyn stuck partition issue here as well because it relied on Brooklyn streams to populate the Bloom filter. Along with this, the debuggability was also a challenge. So if we have to debug why a member is not being returned as restricted, we have multiple places to look. We have to look at the Bloom filter, the cache, and the Espresso database. With DaVinci, it was quite simple to set up. The operational overhead is not much. We just had to ensure the data is in parity with the Espresso source of truth because DaVinci would be a derived store on top of Espresso. For Bloom filter bootstrap time specifically, we did not get any gains because it was using the Brooklyn streams. But in case of DaVinci, we saw a huge decrease in the bootstrap time and lead change propagation by more than 80% with default settings. We further optimized this with few tunings and overrides and were able to achieve less than 10 minutes on a new host. Um, the default Bloom filter implementation also didn't allow removal of entries. This means that as with time, the false positive rate would also increase, and we would be making more remote calls, further adding to instability. So we decided to go ahead with DaVinci using Venice. So this is the like third generation architecture. This was launched 2 months back, completely ramped in production, and so far we haven't seen any issues with Venice. So in addition to the prototype that we had, During the prototype, we just used a Venice push job to populate the Venice stores. Um, During the re-architecture, we added a Venice online producer in the data management system, which writes to Espresso source of truth. So this ensures, as we are writing to source of truth, we are also propagating the same information to Venice. And to make sure we have the data in parity in both Venice and Espresso, we consume the offline snapshots in HDFS and create a remediation job which calculates difference between the two stores and also formats it as per Venice requirement for an incremental push if required. So far, we haven't seen any disparity, but if we see a disparity using incremental push, it would be quite easy to remediate the Venice store. The DaVinci client that we used was off-heap. We didn't notice a very significant increase in uh, on-disk versus off-heap, but off-heap was performing better. And our dataset is itself not quite big, especially after the schema consolidation we did, which is less than 7 GB. So off-heap is good for now. So here are some key highlights and optimizations that we did as part of the architecture. So first of all, we made sure the schema is optimized for reads and is very space efficient. So earlier in the second generation, we had a different data structure for each kind of restrictions. So same member ID was being replicated in multiple places. With consolidation, we were able to decrease the memory footprint from 18 GB to 6.5 GB. We used the Venice online producer, which made sure we didn't have to write up and maintain a nearline pipeline to populate the Venice store. We also used the write compute feature, which was talked in the last session. We require this because our schema is not optimized for writes. Because the schema itself has several fields for different kinds of restrictions, it is very much likely different processes can try to update the same record. So to make sure the data is consistent with multiple processes trying to update the same record, we use the write compute feature, which supports logical timestamps. So it resolves conflicts based on the write timestamp, and the clients basically don't have to make sure of the consistency. Along with this, Venice also supports collection merge now. So with collection merge, we are able to add or remove entries to a collection like set or array or map without having to read the field first, modifying it, and then pushing it. So this is especially useful for us because the way we were storing M2M blocks was in the form of an array, and we didn't want to do a read after write operation. So we just provided the member IDs that add a new block, and Venice took care of the rest. We were able to reduce boot up time drastically with default settings on a new machine. The boot up time was 17 minutes. Earlier, it was 35 minutes. And on old machine, which had some of the data on disk, the boot up time was 7 minutes. We also did some tunings like increasing parallelization, rate limit, and consumer pool size. After all these tuning, we were able to reduce the bootstrap time on a new machine to 8 minutes and old machine to 3 minutes. Since Venice is a derived store for us, we needed to make sure the data is in parity with Espresso source of truth. So we leveraged the Venice ETL and Espresso ETL to create a job and also create an automated way of doing incremental push in case we find any difference. Right now, it is not completely automated. We have a step in between to make sure the difference is actually valid and not related to data issues. Along with this, for online validation, we have a setup where we have still deployed the old architecture on few hosts, and the new host is basically forwarding the request to the old host and comparing the responses. So this will make sure we are not regressing after we have re-architected the entire filtering platform, And it will also highlight issues which can arise because of ingestion delays in Venice or data corruption in Venice stores. So another thing that we noticed during prototyping was because of large batch size, we were seeing high max and P99 latencies. So on further deep dive, we got to know it's because of the batch get that we are going to DaVinci. So we broke the keys into batch sizes of 500, concurrently getting them and merging them back. So this helped made sure our latency is well within 2 millisecond P99. So here are some of the differences that we see with generation 2 and generation 3 after moving to DaVinci and Venice. The biggest win for us was no expensive runtime operation at steady state, like GC. We also didn't had any deployment concurrency limit, so we can scale up as LinkedIn grows. Our lead change time wouldn't increase with increase in organic traffic. We also saw a decrease in client timeouts, probably explained by lower thread wait time, and the inbound errors as well, which increased the enforcement coverage by 15 million per day. We also had lesser memory footprint, which in total led to 6 terabytes of memory savings. Talking about specific parameters, the total deployment time per data center was reduced from 10 hours to 35 minutes. So we were able to roll out any changes within few hours. Earlier, it used to take few days. The deployment time per machine was 35 minutes earlier. After DaVinci and further tuning, on new host, it is 8 minutes, and on old host, it is 3 minutes. We also saw a decrease in client timeouts, reduction around 90%, and inbound errors as well. Thread wait time can be explained because of lower amount of GC and GC time being used by the application after moving to DaVinci. And because of the schema consolidation, we saw a memory footprint reduction from 20 GB per application to 6.5 GB. Yeah, that's pretty much it.